Welcome to this Honors Physics podcast. We'll be taking a look at a few practice problems here having to do with circular motion and centripetal force. There are 6 of them, and if at any point in time you need to pause, rewind, do what you need in order to understand these problems. So the first problem is a loop-the-loop. We have an energetic father who places his 20-kilogram child on a 5-kilogram cart, which is attached to a 2-meter long rope. He then holds the other end of the rope and spins the cart and child around the circle, keeping the cord parallel to the ground. That is very important, that it's parallel to the ground. If the tension in the rope is 100 newtons, what is the linear speed of the cart? So if we can imagine what's going on physically here, we have this circular path, and we have the father right in the middle here. Dad is right here. And dad is attached to a string, and the child is right out here. And the child is traveling in some sort of loop going around this way, and we know that this distance here is 2 meters, and we know that the total mass of the child and the cart over here is 25 kilograms, and we also know that the tension here is equal to 100 newtons. Now, all of these circular motion problems are going to be basically the same. You're going to have to follow kind of a set of circumstances or a set of routines when we go through this. The first thing to do is to draw a free body diagram of whatever it is that's moving around in a circle. So let's think. This is a top-down view of our situation, but our child is moving around in a circle, and it matters then what all of the forces are on the child. So let's take a look at a cross-section of the child. The child has a normal force up, and we're going to include the child and the cart here. Our normal force is going up here. We have a gravitational force or a weight force going down this way. And we have, if I'm looking at the child from this location and I'm looking from this direction, we then also have a tension force going here. Now, it is incredibly important that you do not draw our centripetal force on our free body diagram. So we do not draw our centripetal force on the free body diagram. What we should do, however, is identify the direction that we are accelerating. So at this point here, we know, separate of the free body diagram, like somewhere off to the side here, we know that our acceleration is inward, right? Because everywhere our acceleration is inward. So at this point in time, our acceleration is along our tension. And so what that means is that we can figure out step 2, which is to determine which forces are in the same or opposite direction of our acceleration. So really, we're determining which forces matter. And so we'll see then that our normal force does not matter for our centripetal force, and our gravity force doesn't matter for our centripetal force. The only one that matters is our tension. Now, sometimes these other forces might matter. If, for instance, this center force here was a frictional force, the friction force, don't forget, depends on the normal force. So the size of the normal force might matter if this is a frictional force. But we know that the tension force doesn't depend at all on the normal force, especially when we have our cord being parallel to the ground. So we don't have to worry about any of these other forces, and we can just ignore them here and here. Okay, that's kind of nice. So then our step 3 is to write, oops, I can't spell, I do promise. Our third step then is to write our net force expression, write F net. And so we know our acceleration is inward, so F net is equal to any of my inward forces minus any of my outward forces. So here, our inward force is our tension force, and there is no outward force. Now, the fourth step then is to use Newton's second law and solve for, we're using our Newton's second law of rotation though, and I'll explain what that is in just a second, which leads us to step number 5, which is solve for whatever we're doing. So Newton's second law of rotation basically says that this is equal to ma, but remember, a in rotation is given by mv squared over r. So then we can say this is also equal to m times v squared over r. And so what we have now is we have this situation where this can go away. We can ignore this now, and we can ignore this now, and we know that our tension force, which we have a value for, is equal to mv squared over r. And so now we can just solve. We're looking for the linear speed of the car, so we're trying to solve for v, so let's algebraize this. We get that v, if I bring the r over here to the top, bring the m down here to the bottom, and then take the square root, we have that v is equal to the square root of r times our tension force divided by mass, and that's all inside the square root here. And so that's then the square root of 2 times 100 divided by 25, which is the square root of 8, which is 2.83 meters per second. 2.83 meters per second. Okay, so that's the linear speed of this cart. Now here's another example. We have a car, a 1,500 kilogram car that is traveling and making a left turn around a curve of radius 50 meters on a level, that means it's unbanked, that's flat, road without sliding. We can assume that the friction coefficient between the tires and the road is 1.0. That's pretty close to accurate for most tires as they come into contact with the road. So let's see what this looks like. So here's our road. It's making a left turn like this. And our car is somewhere down here. Here's our car from the top view. It just looks like kind of a box. It also helps me because I can just draw that. And our car is going to go up and go around like this. And so that means that for this section from here to here, this is a circular path. This is a circular path from here to here. And that's what we'll assume. When we have turns like this, we will assume that the actual location of the turn is a circular path. Now, the curve of radius 50 meters, that means that if I were to make this whole thing a circle, and it would lie along this, that would mean that this radius right here, r, was equal to 50 meters. So let's take a look. We have step one, which is to draw our free body diagram. Okay. So at the location that it enters here, we are going to have a normal force up, Fn up. We will have a gravitational force down, Fg, or weight going down, and going to our left, right? Let's think about it like this. If we were not to have a friction force, we would slide this way, right? And so then our friction force is pulling us this way because our friction force is changing our direction to pull us in toward the inside of that curve. So we have our friction force going in, our normal force going up, and our gravity force going down. Now we should figure out what a few of these are. Our gravity force is equal to mass times g, so that's equal to approximately 15,000 kilograms. Kilograms meters per second squared, also known as the Newton. For those of you that are keeping track, 15,000 newtons going down. Because it's not accelerating in the up or down direction, we know then that this is also equal to 15,000 newtons because we have to have our net force equal to 0. And our friction force, remember, is going to equal mu times our normal force. So this will also equal, fortunately for us, 15,000 newtons. Okay? So then step 2 was to determine which forces matter. Now our acceleration is this way along the same direction as our centripetal force as our friction force. So that means the only force that matters for our net force expression is this one right here. Now remember, the normal force did matter because of this relationship here, but it doesn't matter for our net force expression, which is the next step, right? Our F net. So F net will be equal to our frictional force, which will be equal to ma, which is equal to mv squared over r. That's using our next step, which is to invoke Newton's second law of rotation. And so now we know that we are solving 1,500 newtons equals mass times v squared divided by r. And so our v will be equal to the square root of, 15,000 divided by 1,500 is going to be 1,000 times our radius, which is 50. And so in taking into account all of those things right there, we end up with a maximum speed that we can have of, let's see, Vmax is going to be equal to about 22 meters per second. About 22 meters per second. There's some rounding there, but about 22 meters per second. Now what that means is that if we were going faster than that, we would actually fly out, because this 15,000 here is the maximum that our static friction force can be. So we would need more than 15,000 newtons to keep us in a circle of radius 50 meters if we were going faster than about 22 meters per second. If we're going slower than that, our friction force can decrease, and that's perfectly fine. But if we're going faster than that, our friction force would have to increase past what it can actually do. So that can't happen. Okay, next problem, we have a Ferris wheel. 95 kilogram person on a Ferris wheel of radius 40 meters. How fast would it be traveling if the person felt weightless? That means normal forceless at the top. So let's go through our steps. So first, draw a free body diagram. Well, let's see, at the top, we are going to have a normal force, and we're going to have a gravitational force, Fg, going this way. So when we feel weightless, remember that means that we have no normal force at the top. So that would mean that this is equal to 0. Now this gravitational force down here is 95 kilograms times 9.8 or times 10, which is going to give us 950 newtons going down. So what we're saying is that we want this normal force to be 0 and the gravitational force to be pulling us down with 950, and for that to be the only force that's pulling us. What we should remember is that at the top of this circle, our acceleration is down this way. So in general, at the top of our circle, our F net will be equal to our gravitational force minus our normal force. But if this is 0, right up at the top, then we would have this equal to just our gravitational force, so m times g, or in this case 950 newtons. Remember, if we invoke Newton's second law here, this is equal to ma, which is equal to mv squared over r. And so we're going to set this 950 equal to mv squared over r, which would then give us, let's see, 950 is going to equal 95 times v squared divided by 40. So our 95 cancels out with 95 on this side, and we're left with 400 equals v squared. So this thing would have to be traveling at a whopping 20 meters per second. 20 meters per second. So that would mean 20 meters per second, realize, is just about 40 some odd miles per hour. So that would mean that on this Ferris wheel, you're traveling 45 miles an hour. That is incredibly fast. Now think about it like this. If we reduced the speed, we would be reducing the net force, right? Because our net force is equal to mv squared over r. So if we reduced our speed to lower than that, we would reduce our net force. The only way we can reduce our net force is by increasing our normal force. So this is the absolute fastest we can go without flying off, right? Without flying off, because our gravitational force can only be 950 newtons. And so now we're looking for how heavy they would feel at the bottom. Well, at the bottom, let's take a look. Our free body diagram has a normal force going up, and we have a gravitational force going down. So this is still 950 newtons. And now our F net is going to equal our normal force minus our Fg, right? Notice how at the top it was Fg minus Fn, at the bottom it's Fn minus Fg, because now our normal force points in the same direction as our acceleration. And that's going to equal mv squared over r. Now we know exactly how much mv squared over r is from the top. That is 950 newtons. We know that our Fg, this is 950, so what we have is that our normal force minus 950 is going to equal 950, and so take a look at the result of this. Our normal force is equal to 1,900 newtons. Now, typically, our normal force is equal to our gravitational force. So when we travel in such a speed as to be weightless at the top, that means we're going to feel twice as heavy at the bottom. 2 times our normal weight. 2 times our typical weight, I guess is the better way to say it. 2 times our typical weight. Okay, and the same concept here applies on a roller coaster too. When you've got a situation where you feel weightless at the top, you will definitely feel heavier at the bottom, because weightless at the top means that you're traveling with a fast enough speed that at the bottom your normal force must be bigger than your gravitational force. Okay? So we have another friction problem. We have a coefficient of friction of 1.2, a bug on this turntable, and we're asked to find how far out the bug can travel without slipping. When we draw our free body diagram, and let's just say that we have our record here and the bug is somewhere over here. So that means that we have a normal force going up, we have a gravitational force going down, and we have a friction force going in. We're hoping that it won't slip, so therefore it is going to be a static friction. And so we have this is mu times our normal force. Now here's the tricky thing. We weren't given a mass. Mass equals, we don't know. So let's see if we can do it. Our frequency in RPM is 78. So to get this into hertz or revolutions per second, we divide it by 60. We end up getting that it's 1.3 hertz. And remember that because frequency is inversely related to period, that means that our period is going to be 0.76 seconds, 0.769 technically, but that's fine. Now, how does this help us? Well, the only force that's going to be a part of our centripetal force is the acceleration here, or is sorry, not the acceleration. And I apologize for what's going on with the screen right now. Let's see. There we go. Fixed. Is the static friction force, not our acceleration, because our static friction force points in the same direction as acceleration. So if we write our F net expression, F net is going to equal our static friction force, which is going to equal mu times our normal force, and invoking Newton's second law, that's going to be equal to ma. Now, this is where we're going to have to play a few tricks. So first off, we know that our gravitational force is equal to mg. And because we're not flying off of the turntable or flying into the turntable, we know that our normal force then will also be equal to mg, which means our static friction force is going to be equal to mu times mg. So that's nice, because then we can say this is mu mg equals ma, and then voila, our masses cancel out. So we're left with the expression to solve that mu times g is equal to acceleration. Now remember, in general, centripetal acceleration is equal to v squared over r, but v, in general, is given as 2 pi r over t, because remember, we also weren't given our velocity. So if we do 2 pi r over t, in here, that gives us 4 pi squared r divided by t squared, and this may look familiar from the last class. And so we can set now this equal to mu times g. Mu g is equal to 4 pi squared r divided by t squared. And when you solve this, we end up with a radius of 0.17 meters is the maximum that the bug can be at, 0.17 meters. So about 17 centimeters from the center of the record it can go. Now, interesting thing about 78s, a 78 has a 10-inch diameter. A 10-inch diameter means that we have a 5-inch radius, and 5 inches is approximately, the conversion is 2.54, so this is about 12.5 centimeters. So if the bug were to go as far as it possibly could, it would actually fall off of the turntable. That's it for the first video here. Tune into the next video for 2 additional problems.